All right, yesterday we talked about the Diels-Alder reaction, and we had an introduction to it. And we said a Diels-Alder reaction is a concerted cyclization reaction between a diene and a dienophile where we form two new sigma bonds in the process, and we create one new pi bond in the process. So it's a completely cyclic reaction. And we went through and we saw a few examples of these where we can use all sorts of different dienes, but the key thing was that if we compare this S-trans versus S-cis, it has to be S-cis. So if it's locked into an S-trans conformation, this reaction won't work at all. And then we went through and we talked a little bit about stereochemistry, and we're going to start working on this more today. And I wanted you guys to think about it a little bit with the problem of the day. So in this reaction here, we've got our S-cis diene. We've got our cis dienophile. And we said that if your cis dienophile is, or I guess if your dienophile is cis, your cyclized product will be cis too, right? And we said we can kind of explain this by looking at transition states. And I know my transition states drawings aren't the best. I'm trying to work on my artistic abilities, so I added some nice shading. Right? So this is the top-down view. This is the front or top view, so if you're looking down on top of it, this is our diene. In the back is our dienophile, so that's perspective-wise behind the diene there. Let's try to draw a little bit different view so that we can make more sense of this. And this one I'm going to do a side-on view. So if you think about it, I always think of it, it's kind of cheesy, but I think of it as a spaceship. So our diene is on top. And in this case, our dienophile, let me actually move this a bit. Our dienophile is on bottom. And then we're forming some new sigma bonds between this position right there. So it's kind of docking with the diene. And then we're forming a new, we're breaking this pi bond, breaking this pi bond, breaking this pi bond, and breaking this pi bond. So you can think about this as just kind of landing on top of one another. We're going to talk more about the preferred geometry for the diene, or the dienophile, a little later. But for right now, you can just think of it primarily as a docking type mechanism. And when you do this, you can look at it a few different ways. But now our hydrogens are pointing up, and our cyano groups are in the back pointed down. Let me actually draw this in here and here. So we've done a top-down docking sort of thing. And then we said that if you go through and you have a trans dienophile, like we showed here, that your product will also be trans. And in this case, there's no internal mirror plane or plane of symmetry, so we're also going to be concerned with an enantiomer for this one. And so let's try drawing that side-on view for this one too, just so everybody can get a different perspective of this. So we've got our boat view, where we're doing that top-down approach. And again, our dienes on top, our dienophiles back behind there. And now let's see the side-on view and see if we can do the same sort of thing. So in this example, we'll have our diene again on top, our dienophile down below, and I'll have one cyano group here, one cyano group over here, and then protons here and here. And we'll go through and we'll connect our new sigma bonds. Sorry, this should be a single bond between here because we're showing the transition state. And then we're breaking this pi bond, so this should be dashed, this should be dashed, this should be dashed, and that should be dashed. So in this case, it doesn't matter the geometry of this, right? This could be flipped either way. So that's why we're getting a set of enantiomers there, is one side's not favored over the other. So let's draw the product we would get out for this compound, and then we'll continue on to new material. Yep. So we've got two protons out here, And then we've got a cyano group here and a cyano group down there. Oops, sorry. Thank you. Somebody caught me. Cyano group here and a proton there, right? So it's almost like two legs sticking down and two legs sticking out for this one. All right, so now let's do another practice one, and we'll see if we can do this without even drawing the transition state. Do you want me to scroll down?
It's okay, I'll look at her. Thank you, though.
All right, so let's take this diene. This is our last example for this sort of stuff. And this time we're going to have a tetra-substituted alkene as our dienophile. What will our product look like? Yeah, in this case it doesn't really matter, right? So let's go through and just do the arrows for this one and say, all right, we're going to form a new sigma bond between there and there. So this pi bond will jump over, this pi bond will jump over, this pi bond will jump over. And we end up with a cyano group pointing up in each position and one also pointing down in each position. So is there stereochemistry here?
No.
Why not?
Because it's also.
Is it meso though? This is one thing people get confused on. Meso compounds are different than molecules without stereocenters. If we look at these positions, they're not stereocenters, right? They've got two equivalent groups attached. So this compound isn't meso, it's just simply achiral. So that's a fine distinction there. All right, so we've covered stereochemistry for our dienophile and our cyclized product. One thing you may have noticed in all of these examples, I've got a cyano group. All right. Do you guys think cyano groups are electron donating or withdrawing? Withdrawing. So with the Diels-Alder reaction, you normally have to have some sort of electron withdrawing group on your dienophile, at least for a normal Diels-Alder reaction. So most of the examples in the books will have some sort of carbonyl group or a cyano group or something that is electron withdrawing. And what this does is it lowers the activation energy and allows this reaction to occur much more easily than if you had an electron donating group or even no electron withdrawing groups on there. Does that make sense so far? All right, now that we're going to do a more challenging problem, and I want you guys to work on it for a bit. So challenge. All right, for our challenge problem, we're going to use a new diene. Let me try to emphasize this double bond here. So this is our diene, and we're going to react this with this dienophile. And in particular, I want you guys to try to draw the transition state for this, just like we did on the problem of the day. I would maybe try to draw it as the boat view. So that top-down view, I know it's harder to draw that way, but in this example, it will make more sense if we draw it in the boat view. You can draw it either way, but you'll see the stereochemistry will make more sense with the boat view. So I'll give you guys a minute to work on this. I'm going to actually lower this picture down too, so we have more room. If you want, I can get you started with the boat view, too, if that helps. So I'll do my artistic shading here. So we've got one methyl group that's cis, so I'll call this Me. Another hydrogen that's trans. And then we've got this and this. I'm going to actually blow this up and make it even bigger too. Really emphasize the size here. Oh, sorry. This should be a methyl over here. Thank you. Let me even... There we go. So that's our top-down view. We have to add the group behind it now. So what I'll do is do this one much smaller because we know it's pointed back. Right? Now let's connect all the dots in the transition state. And so we're forming a single bond here. We're forming a single bond there. We're breaking this pi bond, so we'll have that as a dash. We're breaking this pi bond, so we'll have that as a dash. Breaking this pi bond, so that will be a dash. And we're breaking this pi bond, so that will be a dash. Does that make sense? Kind of how we're looking at it? One thing that confuses people is how can we tell if it's cis or trans? Well, for the cis one, for this methyl group, it's cis to this position, right? So if we compare methyl to this alkyl group, it's cis. If we can compare this methyl group over here, they're trans. So that would correspond to that trans side. So this is kind of like our boat conformation. And so we've got one methyl group sticking out in a way and one sticking kind of up towards this other proton. All right, so if we do this, we get a product that looks a little funky. So I'm going to label this as our transition state. So we've got a cyano group pointing out here, cyano group pointing out here, here, and here. We've got a methyl group pointing here, a hydrogen pointing here, then a hydrogen pointing over here, and a methyl group pointing down here, right? This is kind of a confusing way to look at it, but if we think about it as our eyeball is looking down on top of this now, we can draw it slightly differently, right? So let's draw the two-dimensional view right above it. We know that this is, I forgot the double bond. There's our double bond. So if we go through and we draw this as a two-dimensional view, the top methyl group is going to be a wedge. The bottom one will be a dash. It's okay. So one should be a wedge, the other one should be a dash. And then we have all four of our cyano groups. So can you guys kind of see this, how this boat conformation can be a little helpful, especially when we're looking at the stereochemical configuration in this position on the top and the bottom of the ring. Specifically, if we've got a trans group, like on the bottom, if it's trans, it will usually be a dash. And if it's cis, it's going to be a wedge. And so on our problem of the day, we saw an example like that, and we're going to try to work through the problem of the day here in a little bit. But this boat, you want me to draw the side view? Okay, let's do that one. It always depends on how your reaction's laid out. So if let's say your dyne is facing so that its open end is to your right, that rule will hold, but obviously if it's flipped, the rules will be changed. So as long as you're consistent, that rule will hold.
Unless you say draw this transition state, do we have to draw those different views if we don't need to?
I always recommend that people do, because if you try to memorize rules, you'll forget them in a week. But if you try to remember the transition state, that concept sticks with you a little longer than memorizing rules.
More about the boat conformation. I don't know that. I see it before I see that boat.
Well, let's draw the side-on view too. And in this example, we said that the top one is going to be, sorry. So that's our diene on the top, right? And then we've got our, our dienophile underneath. And then we'll connect all of the dots here too. Sorry, no, that's a long stretch. So this would be an example of the side-on view. This is the top-down view. But either way, they both form that same product. If you can see, though, that if you draw the side-on view for this one, it doesn't really explain the stereochemistry at these two positions on your diene. The boat view does a little bit better job of showing it for this one. So I actually prefer the boat view. The book prefers the side-on view. Whatever works for you, stick with what works for you, though. If you have to draw both, you can draw both, too. Yeah, Kareem? Whatever works for you. I prefer to have some sort of three-dimensional configuration, though, and not just two-dimensional. On the problem of the day, I just wanted to get you guys thinking about the transition states, but we'll go through and do this same sort of process with the problem of the day, too, and it should make more sense.
So two-dimensional would not be useful.
No, if I ask for the transition state, I prefer a three-dimensional view, because that gives you stereochemical information. A two-dimensional view doesn't very well. All right, so let's kind of change gears and talk about what's going on with this whole docking mechanism. Let me shrink this up a bit. So at the molecular orbital picture, or molecular orbital level, we have a very specific thing happening here. So we can see our HOMO of our butadiene, and in particular, we know that this is a HOMO because it's showing this double bond between the two red lobes. So they're in phase, they overlap. And the double bond between the two blue lobes in the back, they're in phase, so they overlap. So we've got two sets of double bonds in our butadiene. That means that this is the HOMO. And then the LUMO for the ethylene means that we're one energy level above that double bond. So that means we've added a node here, which is a little strange to think about. But we said the other day in class that we keep on adding nodes when we're trying to go up energy levels. So in this case, when these overlap, we can actually have these two lobes in phase, the blue lobes in phase and the red lobes in phase. When this happens, we actually get a hybridization where these start to shift, and our new product looks a little bit like this. So this is what's going on at the molecular orbital level. Like I said, it's kind of this docking, and the reason it has to dock face to face or kind of edge on is because we have to overlap these p orbitals in phase in the right way. It's not going to be two-dimensional, a side-on interaction. It's always going to be some sort of docking interaction. This is why. It's all about the molecular orbitals going on here. If you read through your book, you can read about this quite a bit more with all of the other cyclization reactions, but I'm going to kind of leave it here because the Diels-Alder reaction is the most important, or arguably most important reaction in this section of the book. All right, so now let's take it one step further and start getting into kind of challenging Diels-Alder problems. Let's take a look at this problem. This is a really common diene. It's called cyclopentadiene. It's very useful as a diene for Diels-Alder. Does anybody know why? Not ring strand. Can this go to S-trans? It's locked as S-cis. So anytime we can get a locked S-cis conformation, it's going to be really, really good for Diels-Alder reactions. And we're going to react it with the reagent that we saw on our problem of the day. which is a good dienophile because it's got those electron withdrawing groups on there. And now what we need to do is we need to analyze, all right, what product will this go to? We've got a couple different options. So let's take a look at the different options that we're going to get here. There's one option called Endo Addition. And what Endo Addition means is, let's do this side-on view for the reaction, this docking that's occurring. So we've got one piece down here. We've got the other piece, whoop, let me draw this a little better. Other piece down here. And what we're going to do is we're going to connect our positions again. So we've got a sigma bond forming there, right? Then a sigma bond forming over here. We broke this pi bond. We broke this pi bond. We broke that pi bond. And we broke that pi bond. So can you guys kind of see that transition state? You're not feeling the side view? I'll draw the other view here next, but let's compare this to the alternate too, so it maybe makes more sense. Oops, sorry, I mixed this up. This is actually exo, I apologize. I had them flipped in my notes. This is Exo Addition. And then we'll do Endo over here. Sorry about that. I get too excited when I lecture, I guess. All right, and then our other addition product, we'll have our dienophile facing the opposite direction. Let me actually lower this down a little bit too, so we can really emphasize its position. All right, so we're going to form a sigma bond between these two carbons and these two carbons. So now that dienophile is practically underneath the cyclopentadiene. And then we're forming a new, or breaking that pi bond. I'm going to break this pi bond, break that pi bond, and form this pi bond. So with an endo addition, the dienophile is perfectly underneath. They're stacking like pancakes on top of one another. If we think about the exo addition, they're a little bit offset. One pancake is a little off to the side, the top pancake's a little off to the other side. So this is more of an edge-on type stacking. The endo addition is just flat, perfectly on top of each other. And so we've got to ask ourselves, which one is going to be more preferable? And this becomes a really challenging problem, I think. What do you guys think about the exo addition in terms of sterics? Is this more favorable or less favorable due to sterics? More favorable due to sterics. So exo addition is sterically favored, but sterics aren't the entire picture with chemistry, right? We've got this bounce between sterics and electronics, right? The interesting thing is, if we look at each of these, we're breaking these two pi bonds in the diene, and then we're forming a new pi bond. So we're breaking and making a lot of pi bonds within our diene. That takes a considerable amount of energy. So we have to think about, well, how can we stabilize this sort of transition state if we're making and breaking all of these pi bonds? Well, the preferential thing is for these to be close to an electron cloud. That will stabilize the transition state. And so if we look down underneath for the endo transition state, we've got these electron withdrawing groups with a high affinity, or a big electron cloud underneath here. So this actually stabilizes the making and breaking of all of these bonds. Where over here, they're too far away to have any sort of impact with these bonds being made or broken. So electronically, endo addition is preferred. So let's write these both down. Electronically stabilized, specifically this whole section. I'll try to highlight it. We'll see if it shows up. You guys see that on the screen? Yeah. So that electron withdrawing group being right underneath those pi bonds is very, very stabilizing. So typically when we do Diels-Alder reactions, we get our endo product. And let's kind of compare the two different products we would get out of this. Is this transition state okay for the view right now? The boat one we'll go back to later, but for right now, this kind of explains endo versus exo a little bit better. Do you want me to show the other transition state?
Sure.
Yeah,
All right.
I don't like this
What
one.
happens to the other two carbons at the top of that ring?
We'll show that next. Yeah.
Show project.
Let's show the boat view for each of these. Nope. So for this one, we've got this bond being made, this bond being made, this pi bond being broken, this pi bond being broken, that pi bond being broken, and this pi bond being made. So that's our exo addition. So you can see how that dienophile is kind of pointing away, where if we compare that to the endo addition, oops, shoot. With the endo addition, shoot, I got to really exaggerate this. It's pointed the opposite way. So it's underneath. All right, so these are our two transition states. All right, now let's go through and draw our products that we would get out of these. And whenever you have, oops, shoot, I forgot the bridgehead. Sorry, guys. So because we had cyclopentadiene, it's got this center bridgehead carbon up here. So now let's go through and draw our products. I know this can be pretty challenging to see, so bear with me.
Do we need to draw this?
If you don't want to draw it, it's fine. I'm trying to give you guys the kind of three-dimensional view for this. So do you guys see how our dienophile is pointed more in the equatorial position here? And these protons are pointed in the axial position down. This is what exo means. Exo means that it's pointed kind of away from our bicyclic ring system. And we'll compare this to our endo product. Oh, let me fix this a bit.
I feel like he's drawn a dolphin.
I wish I could draw a dolphin. All right, so now if we look at our dienophile, I'm going to highlight our dienophile. In this case, our dienophile will be highlighted in yellow. It's pointed away from our ring. If we look at our dienophile that's added on now, it's actually pointed kind of towards the ring. So in this position, it's equatorial. And in this position, it's axial. So most of the time, we end up observing the endo product. Chemists using modern techniques can exclusively get endo or exo, but if you were to run this without some of the newer catalysts, you would pretty much, probably 90% of the time, observe the endo product. So the endo product is usually favored. And so just like we were saying, endo products are typically favored because it's electronically stabilized here. This one has no electronic stabilization. All right, so we've got our two different products here. Now let's go back and take a look at our problem of the day. I feel like we've laid the groundwork so that we can go through and analyze our problem of the day in much more detail. So in our problem of the day, I think most of you were able to identify the diene and the dienophile, but now let's take a much, much closer look at the transition state. Yeah? Model kits help, and I'll show you guys how model kits will help with our problem of the day example. So let's take our diene. Most of you guys said that you thought the diene would look like this, right? No. I was just curious if anybody did the cysts. I didn't get a chance to see everybody's, but I think most people drew the trans just because inherently it looks more stable. And then for the dienophile, we had this exact same ring system that we had seen on our last example, right? So a lot of you guys had this. But now let's go through and examine everything that's happening stereochemically. So let's draw the transition state, and I'll draw both the side-on view right, so that's our diene. And then I'll draw the dienophile underneath. And in this case, we know that it's going to favor this endo form. So we're going to form a new sigma bond between these two carbons and these two carbons. We're going to break this pi bond. We're going to break this pi bond. And we're going to break that pi bond. Does that make sense? So this would be our side view. So side on view. Now let's compare this to our boat view, that top-down view, and see if we can get a little bit more information out of what's going on here. And we're going to make bonds between this position. We're going to make bonds between this position. I'm going to break these pi bonds, and then I'll add in the methyl group next. All right, so the methyl group on our diene, should it be pointed into the boat or away from the boat?
Away.
So I heard people say away. Why is that?
Oh, because it's a dash.
Because it's a dash. So if we look at the product, we can get a clue. But let's try to rationalize this. So I'm just going to trust you on this. I'm going to say, all right, let's say CH3 is over here.
It's more stable that way too.
It's more stable. We've got a hydrogen here and a hydrogen here. The other thing we can think about, too, is let's compare these bonds here to here. They're trans to one another, right? If we look at our product, our top alkene on our diene is trans. So this methyl group has to be pointing away from the boat. If we had a cis diene where that methyl group was cis, then it would be pointed where that other proton is on that carbon. So we have to pay attention to where the protons are here.
So it's going to be places where we could
Nope, remember endo is simply referring to your position of your dienophile. Is it underneath pointing down like this or up like this? It's not looking at methyl.
But that's endo.
Yes, this is endo. So let's take a look at this with our model kits, and I decided to try to draw this, or make it for you. So on the side-on view, we've got it like this, right? And then I'll put the dienophile in the back, underneath like this. So when we're making a bond, we're going to attach positions between the two carbons there. So it's kind of a pancake stacking interaction. We can also think about this with the side-on view, where this methyl group is pointing back and this is coming underneath. It's just docking like this, right? So now let's quickly try to swap out some of these bonds here to form our product. So if you guys have a chance to do this at home, I'd recommend doing it. It makes a lot more sense when you see it. So let me quickly, or as fast as I can, we're going to switch positions here. So now we've got our pi bond on the other position. Oh, sorry guys. Going to form a new sigma bond here. Then I also have to swap these out too. Excuse me, guys. This is a lot of popping, I know. All right, we're getting there. I just want to give you guys an idea of what this looks like three-dimensionally. That one here. Sorry. I know this isn't the most engaging portion of the lecture, but this is something that's hard to see unless you see it three-dimensionally. Ugh. All right. So now I've done the docking. So this, can you guys see how if we look through it this way, the dienophile is in the back, and the diene is in the front, right? So this is the endo. And then let's look at it point on, right? And I'm going to scroll down the page. Now it makes a little bit more sense, right? If we look at this methyl group, it's pointing back, right? If we look at these two protons here, they're both pointing forward. And then this dienophile, we don't have it shown here, but these could be represented using dashes as well. So if we look at it, this would be an appropriate front bond view for this molecule. And it makes sense too, because if we think about this boat conformation, if we're looking down here, these two protons should be sticking up, right? They're closest to our eyeball if we're looking down. So imagine we're doing a top-down view. This methyl group should be a dash, right? Because it's further away from our eyeball than this proton. So just imagine that your eyeball is right above this, looking down on this molecule, right? So I would recommend trying to go through as many of these problems as possible on sapling. Yep.
What if you have your, in the top-down view, the boat corporation?
Uh-huh.
What if you have the, what is this?
The dienophile?
Yeah, the dienophile. What if you had it with the oxygen cut?
So if you had this pointed this way, that would be your exo product. And we said that exo products aren't normally observed. We prefer to have the endo product because these electron withdrawing groups stabilize these bonds being made and broken in that pi system.
Okay, well, in regards to the POD, we didn't know that.
No, we didn't know that for the POD. I just wanted to get you guys thinking about transition states a little bit before we covered it in class.
So, they're always going to be upside down?
Yep, your dienophile is always going to be stacked underneath like a pancake. It's not going to be an edge-on sort of stacking.
Okay.
It's always endo.
As far as we're concerned, it will always be endo. All right. Are you guys ready for something different?
Not really. You gotta put it on the quiz. It's more
So we're going to switch gears a little bit and talk about colors because I like talking about colors.
colors.
Colors, yes.
Like rainbow?
Yes, like rainbows.
Oh, yeah.
Don't get excited, Adrian. He's gonna throw a wrench into this.
All right. Whoa, come on. So I really enjoy talking about colors. A lot of chemists get into chemistry simply because they think the colors are cool. It sounds kind of cheesy and lame, but you talk to most inorganic chemists and they're like, I chose inorganic chemistry because it's pretty. And it's like, oh, that's nice, I guess. But the interesting thing with organic chemistry is it can be really colorful too. And the simple concept is that more conjugation equals a longer wavelength or lower energy absorbance. And we saw this in our UV lab that we did the other week where we were looking at beta carotene and chlorophyll. And if we look at the structure of beta carotene, which I actually have shown below, it's got a huge amount of conjugation between all of those carbons, right? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 double bonds that are all conjugated to one another. So the more conjugation we have shifts this to a longer wavelength light. I know vitamin A is really hard to see above in yellow, but this has fewer double bonds. And then if we go down to the one below that, that's let's see if I can pronounce this, astaxanthin. It's pink because it's got even more double bonds. So every double bond we add shifts it to a longer wavelength light. So it appears to be more red or it gets red shifted. Conversely, we can look at a lot of these different compounds. It gets really interesting if you look at aromatic compounds, and I could talk for days about this, but I won't. If we look at benzene, it's colorless. Has absolutely no color. Same with naphthalene and anthracene. That's because these absorb light in the UV region. They require very, very high energy light. But as soon as we add more conjugation to it, we make tetracene, it turns bright, bright orange. It's a brilliant orange color because we've got more double bonds on it. Interesting thing, why is pentacene all of a sudden going back to purple? Kind of bar trivia. But if we look at it, the interesting thing with pentacene is that these electrons all talk to each other, and then these electrons all talk to each other. The center ring is kind of excluded. So if we look at this, the conjugation for these ones consists of 2 rings talking to each other. Conjugation for this one consists of 4 rings. So even though this one looks more conjugated, it's actually not. And pentacene is a really interesting theoretical compound, but it's remarkably unstable. As soon as you pull this out, it tends to dimerize with other molecules really, really quickly because these 2 carbons are very, very reactive. You can go through and see a lot of these colors on here. Some really common ones are green dyes. So if you work in biochemistry, you'll see a lot of these. And then if you go to like the granddaddy of them all in terms of conjugation with lycopene, this absorbs way out into the red region. And there's a set of rules that's defined in your book called the Woodward Seizure rules, where we can actually try to predict where things will show up. So I don't expect you guys to know this. I just think it's really interesting. I'm not going to like put this on a quiz and say predict the wavelength of this, right? I just think it's neat that if you have 2 double bonds, this has a base value of 217. You add another double bond. Each additional double bond adds a wavelength of 30 nanometers to it. So on this one, we're going to add 30 times 2. This goes to 277. If you've got alkyl groups, they each add 5 nanometers. And then, if you look at the one down here, we've got 2 double bonds, but this double bond is located outside of a ring. So this adds 5 nanometers, and then we've got 2 alkyl groups. But if this double bond is located in the same ring, it adds it all the way up to 39. Why do you guys think this one has more conjugation? Yeah, they can talk to each other. And then we've been talking a lot about Cysts conformations. In this one, it's locked into an S-cis conformation. This is S-trans, and S-cis systems tend to talk to each other much, much better. The one last thing I wanted to leave you with is about the chemistry of vision. And let me shrink this down. This was one last thing I love talking about in this chapter because people say organic chemistry is not relatable. If you look at the molecules in our eye receptors, right, our rods and our cones, they consist of these highly conjugated systems, right? And if we shine this cis bond, the cis alkene, with a certain frequency of light, it will actually cause this to go up in energy level, turn this into a double bond and this into a single bond. And when it does that, sterics say, well, this should switch to trans. And so when light hits our cones or our rods, it will cause it to switch to trans. And our protein can actually feel this molecule moving to a different position. It sends a signal to our brain, says, you just saw this frequency of light. And then this slowly relaxes back down into its off state. So humans have rods and cones. Let's pull this up. But there's an animal. Let me grab my thing here. I'll put this on the class website under the interesting section. It's Why Mantis Shrimp is My New Favorite Animal, written by the Oatmeal comic. And our eyes can see millions of colors because we've got rods and cones. Dogs have two types of color receptors. They can see green and blue. Humans can see green, blue, and red, which is pretty good. We've got an extra red cone. So we can see all sorts of combinations of red and yellow, which is orange, and then red and blue, purple, or red and yellow, which is orange. Butterflies have 5 different types of color receptors, right? So they can see all sorts of colors we can't. But the mantis shrimp is the winner of them all. I'm going to scroll down. It doesn't have 2. It doesn't have 3. It doesn't have 5 like the butterfly. It has 16 different color receptors. So it can see colors we can't even begin to imagine what those colors would look like, right? It can see deep, 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 deep down into the red region, and then really, really, really far into the UV region. And yet it's this little tiny shrimp that lives outside of Australia. And this guy writes some of the funniest comics I've ever read, so I'll post this on the interesting topic portion of the website. But it's just something interesting to think about. They've actually found humans that have an extra receptor in their eye. They're primarily women. And so they can distinguish colors. They can say, well, that red's different than that red, and everybody else is like, those are the same reds. I'm not sure what you're talking about. But some people actually have an extra receptor in their eye. So I kind of wanted to leave it there.